Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is instrument loading effects. Our objective today is to take a look at instrument loading effects and how the act of measuring an electrical quantity can influence a circuit's behavior. Let me begin this lecture with an admission of guilt. I'm guilty of not so much as lying to you, but rather I'm guilty of withholding information from you. Understand I operate under the Kung Fu principle, and that I am always entitled to withhold one move from you lest you at a later date come back and challenge me. Never forget this. Additionally, my withholding of information is essential to your progressive development as a technician. If I was to present you with the true extent of reality as it is currently understood, right up front, we would go nowhere. One can dive as deep as one desires down any rabbit hole of their choosing to find more and more accurate and increasingly complex depictions of reality, truly horrifying in their complexity. Progress dictates we make simplifications and necessitates we use simple models. The comforting news is this: the simple models work. For our level of detail, we do not care about things that only minutely affect reality. Ohm's law states that the current through a 1.2 kilo ohm resistor with a 24 volt drop across it should be 20 milliamperes. When an ammeter reads approximately 19.92 milliamperes of current, I'm cool with the fact that there's a small error. A difference of 0.08 milliamps isn't worth a second glance. Ohm's law is true. Additionally, Ohm's law can be used to predict the behavior of current for different voltage and resistance values. For constant resistance, if I increase the voltage, the current should proportionally increase. For constant voltage, if I increase the resistance, the current should decrease. If I used astronomically high or infinitesimally small voltage or resistance values, the simple linear relationship might break down. Who cares? We normally don't deal with astronomically high or infinitesimally small values. Normally we operate equipment as intended and leave these theoretical boundary regions to those bespectacled nerds in pure science disciplines. If you've been watching the Basic Electronics 1 DC Circuit Analysis playlist in its intended sequence, we've now arrived at a topically relevant junction that I can reveal additional details behind some of the simplifications I've repeatedly employed during the course of this series. You've heard me time and time again say that ideal ammeters are modeled as having 0 ohms of resistance, and ideal voltmeters are modeled as having infinite ohms of resistance. The truth is, they don't. The truth about the truth is, who cares? Ammeters have low resistance. Voltmeters have high resistance. Ideally, a low resistance ammeter placed in series with a component it is intending to measure current through won't unnecessarily present additional opposition to a source. Ideally, a high resistance voltmeter placed in parallel with a component it is intended to measure voltage across won't draw additional current. Quality ammeters and voltmeters do affect circuit properties, but they don't affect it much. Poorly made equipment affects circuit properties, and sometimes these effects are noticeable. Ohm's law states that an ideal 24 volt source supplying an ideal 1.2 kilo ohm resistor would supply 20 milliamperes of current. Now consider an ammeter with 5 ohms of internal resistance placed in series with this 1.2 kilo ohm resistor. The source is no longer seeing 1.2 kilo ohms of resistance, but rather 1.2K plus 5 or 1,205 ohms of resistance. Ohm's law states that current is equal to the voltage divided by total resistance. Substituting in the necessary values, we find the ammeter is experiencing approximately only 19.92 milliamperes of current. What happened to the missing 0.08 milliamperes of current? It's not like that missing 0.08 milliamperes went off somewhere else. It's that the inclusion of the 5 ohm ammeter in series with the 1.2 kilo ohm resistor makes this a new circuit with ever so slightly higher resistance, and the source will only produce 19.92 milliamperes of current. The act of measuring the circuit influenced its behavior. However, it didn't affect it much. I can live with this level of inaccuracy. What about a poorly constructed ammeter with 50 ohms of internal resistance? The cheap DMMs available in the discount rack can present this burden and more to a circuit through which it is measuring current. An ammeter with 50 ohms of internal resistance used to measure current through a 1.2 kilo ohm resistor would present this 24 volt source with 1,250 ohms of resistance. Ohm's law states that the current through this resistor is the source voltage divided by total resistance. Substituting in the necessary values, we find the ammeter is experiencing approximately only 19.2 milliamperes of current. Again, not necessarily a cause for concern. However, if we kept using ammeters with increasing internal resistance, we'd get increasingly inaccurate results. Additionally, consider the original resistance through which we were measuring current. What if the resistor of interest was 50 ohms? In its pure form, Ohm's law states that the current through this resistor should ideally be 480 milliamperes. An ideal ammeter with no internal resistance would read this value. However, an ammeter with 5 ohms of internal resistance would present an additional 5 ohms of series resistance to the source, for a total of 55 ohms. Ohm's law states that this ammeter would experience only approximately 436.4 milliamperes of current. If you used an extremely poorly constructed ammeter with 50 ohms of internal resistance, the 24 volt source would not see 50 ohms of resistance, but rather 50 plus 50, or 100 ohms of total resistance. And Ohm's law states that this ammeter would only experience half the anticipated current draw at 240 milliamperes. This is not good. Although inexpensive, such an ammeter is essentially useless for the purposes of accurately measuring current. In retrospect, maybe the bargain ammeter might not have been such a good purchase. Before we move on to discuss the less than ideal nature of voltmeters, let's talk about voltage distribution in circuits using less than ideal ammeters. Realize the internal resistance presented by an ammeter is a series resistance across which a voltage drop will occur. When an ammeter with 5 ohms of internal resistance is used to measure the current through a 50 ohm resistor produced by a 24 volt source, Ohm's law states that the voltage drop across the 50 ohm resistor is only roughly 21.8 volts. The remaining 2.2 volts would be dropped across the 5 ohm ammeter in series. Again, providing additional proof the inclusion of a less than ideal ammeter in a circuit affects the circuit's performance. Let us now discuss the non-ideal nature of voltmeters. Up to now, I've been considering voltmeters as having infinite resistance through which no current will flow when they are placed in parallel to the load they intend to measure voltage across. That's not really true. Voltmeters are more accurately modeled as having extremely high resistance, and their inclusion in a circuit will affect that circuit's performance ever so slightly. Voltmeters with larger resistance will affect the circuit less. Voltmeters with smaller resistance will affect the circuit more. An ideal voltmeter with infinite resistance will draw no additional current when placed in parallel to an electrical load. A 24 volt source supplying current to a 50 ohm resistor would still continue to provide 480 milliamperes of current. However, consider a voltmeter with 10 mega ohms of resistance placed in parallel to a 50 ohm resistor hooked to 24 volts. The source is no longer seeing just the 50 ohm resistor, but rather the parallel combination of a 50 ohm resistor and a 10 mega ohm resistor. The parallel combination of a 50 ohm resistor and a 10 mega ohm resistor is 49.999750 carried out to 6 decimal places. Is this different than 50 ohms? Essentially no. Ohm's law states that the source would now provide approximately 480.0024 milliamperes of current to this parallel combination, 480 milliamperes of which traveled through the intended 50 ohm path, and 0.0024 or 2.4 nanoamps traveled through an unintended path. 2.4 nanoamps. Is this worthy of even the slightest wrinkle in your shorts? Absolutely not. However, now consider a voltmeter with 5 kiloohms of resistance placed in parallel to a 50 ohm resistor hooked to 24 volts. This subpar voltmeter now presents a parallel path with substantially less resistance than earlier. The source no longer sees just the 50 ohm resistor, but rather the parallel combination of a 50 ohm resistor and 5 kilo ohm resistor. The parallel combination of a 50 ohm and 5 kilo ohm resistor is approximately 49.504950 ohms carried out to 6 decimal places. Is this different than 50 ohms? Essentially no. Ohm's law states that the source would provide approximately 484.8 milliamperes of current, 480 milliamperes of which traveled through the intended 50 ohm path, and 4.8 milliamperes of which traveled through an unintended path. Is this worthy of consideration? Maybe, maybe not. The other piece of pertinent information I've been withholding is this: voltage sources aren't ideal either. It too also has an internal resistance across which more voltage will be dropped when more current is being drawn through it. Is 4.8 milliamperes of additional current enough to tip the scales? Maybe, maybe not. Ohm's law says that an ideal 24-volt source will supply an ideal 50 ohm resistor with 480 milliamperes of current. This is the simplest of circuits consisting of a single source and a single element. Consider, however, a 24-volt source with 2 ohms of internal resistance. In its unloaded condition, there would still be 24 volts between its 2 terminals because there is no current flow through the 2 ohm internal resistance and no voltage will be dropped across it. When the source supplies current to a 50 ohm load, it is in effect seeing the 2 plus 50 or 52 ohms of total resistance. Ohm's law states that the current through the load will be approximately 461.5 milliamperes. We've created, in effect, a series circuit of 2 elements. Ohm's law states that the voltage drop across the 50 ohm resistor will be only approximately 23.1 volts, and roughly 0.9 volts will be dropped across the internal resistance of the source. The non-ideal nature of the source has already seen reality and expectations part paths, and we've yet to introduce a single non-ideal instrument. Along comes a voltmeter with 5 kiloohms of internal resistance placed in parallel to this path. The source is now in effect seeing a series parallel circuit, being the parallel combination of the original 50 ohm resistor and the 5 kiloohm voltmeter in series with the 2 ohms of internal resistance. This means the source will provide approximately 466 milliamperes of current, approximately 461.4 milliamperes of which travels through the original 50 ohm resistor, and the remaining 4.6 milliamperes of which goes through the unintended path created by the voltmeter. With this amount of source current, the resistance internal to the source will drop just shy of 1 volt, and the 50 ohm load resistor will experience only approximately 23.07 volt drop. At first glance, a 50 ohm resistor with 24 volts across it seems like a simple problem, but when you take into account some of the non-ideal behaviors of sources and instruments, you wind up with a sticky, tangled, complicated mess. Do you now appreciate the simplifications I've thus far employed? Keep in mind I've yet to incorporate an ammeter to this mess. An ammeter employed in the following location makes this once seemingly simple problem yet another series parallel permutation. The source experiences a total resistance of the parallel combination of the original 50 ohm resistor and the 5 kiloohm voltmeter in series with a 5 ohm resistor of the ammeter in series with the 2 ohms of internal resistance, for a total resistance of approximately 56.5 ohms. Ohm's law states that the source would provide approximately 424.7 milliamperes of current, approximately 420.5 milliamperes of which travels through the original 50 ohm resistor, and the remaining approximately 4.2 milliamperes of which goes through the voltmeter. With this amount of source current traveling through both the internal resistance of the source and the ammeter, the resistance internal to the source would experience approximately 0.85 volt drop, and the ammeter would experience approximately 2.12 volt drop, meaning the 50 ohm resistor and the voltmeter in parallel would experience only approximately 21.03 volts drop. This is to suggest everything is a little bit more complicated than it seems. When you take into account every little tiny detail, each new detail brings with it a level of previously unseen complexity. We could go on like this all day, but we don't have all day to do so. This lecture, although titled Instrument Loading Effects, is in actuality yet another opportunity to practice series parallel circuit analysis skills. The topical thrust of the title is that a level of observed inaccuracies can be explained using previously acquired electrical theory. Consider the following circuits in their ideal condition, and again, when non-ideal instruments and sources are used to build and measure it. Circuit 1 is a pure series circuit consisting of a 48-volt source, R1 at 90 ohms, and R2 at 180 ohms. Circuit 2 is a pure parallel circuit with a 120-volt source, with R1 at 120 ohms and R2 at 240 ohms. Circuit 3 is a series parallel circuit with a 36-volt source and R1 at 100 ohms, R2 at 120 ohms, R3 at 200 ohms, and R4 at 180 ohms. By all means, pause the lecture and solve for voltage across and current through all components, including source current. If you've been following the Basic Electronics 1 DC Circuit Analysis playlist in its intended sequence, this should be well within your ability to do so by now. Again, visualize circuits at the nodal level and from the perspective of flowing current. Results of Circuit 1 are as follows. V1 is 16 volts, V2 is 32 volts, and source current I1 and I2 are 177.8 milliamperes. Current through elements in series will be the same. I1 equals I2 equals Is. What goes up must come down. E equals V1 plus V2. One can use the VDR, Ohm's law, or KVL to solve for any value. If you obtain different values, please take the time necessary to correct your assumptions. The results for Circuit 2 are as follows. V1 equals 120 volts. I1 equals 1 amp. V2 equals 120 volts. I2 equals 0.5 amps. Source current equals 1.5 amps. Voltage across elements in parallel will be the same. E equals V1 equals V2. What goes in must come out. Is equals I1 plus I2. One can use the CDR, Ohm's law, or Kirchhoff's current law to solve for any value. If you obtain different values, please take the time necessary to correct your assumptions. The results for Circuit 3 are as follows. V1 is 13.2 volts, as is V2. I1 is 131.5 milliamperes. I2 is approximately 109.6 milliamperes. V3 is approximately 22.8 volts, as is V4. I3 is approximately 114.2 milliamperes. I4 is approximately 126.9 milliamperes. Source current is approximately 241.2 milliamperes. This series parallel circuit has source current split between two paths. Is equals I1 plus I2. Source current recombines and again splits between two paths. Is equals I3 plus I4. Since R1 is in direct parallel with R2, voltage across them will be the same. V1 equals V2. I'll call this combo R prime. Since R3 is in parallel with R4, voltage across them is the same. V3 equals V4. I'll call this combo R double prime. A KVL analysis of this series parallel circuit suggests that E equals V prime plus V double prime. If you obtain different values, please take the time necessary to correct your assumptions. Now let's consider these same three circuits when we take into account non-ideal conditions, sources, and instruments. For the purposes of this exercise, let's say we're really slumming and all the sources have 5 ohms internal resistance, and any ammeter used to measure current has 10 ohms of internal resistance, and any voltmeter used to measure voltage has 4 kiloohms of internal resistance. These instruments are not intended for accurate measurements, but rather purposely selected to present some reasonably challenging circuit analysis scenarios. By all means, pause the lecture and determine how these subtleties affect the observed properties of voltage across and current through all components, including source current. Here's where the instruments are deployed, so we're all on the same page. For Circuit 1, the internal resistance of the source and the ammeter, the 2 voltmeters in parallel with R1 and R2, quite obviously changes the nature of our once pure series circuit into an ever so slightly more complicated series parallel circuit. They should still be well within your reach. I'm asking what the ammeter and voltmeters read at their given locations. Be aware that the single ammeter in this circuit would be measuring source current, but it isn't really measuring I1 or I2 because a portion of source current is diverted through the voltmeters in parallel. We'll discuss these subtleties in the analysis. For circuit 2, the 3 ammeters, the internal resistance of the source, and the voltmeter in parallel quite obviously change the nature of our once pure parallel second circuit into an ever so slightly more complicated series parallel circuit. This should still be well within your reach. I'm asking what the ammeters and voltmeter read at their given locations. Be aware that the single voltmeter in this circuit isn't really measuring V1 and V2, but rather the voltage across 2 parallel paths consisting of an ammeter in series with a resistor. We'll discuss these subtleties in the analysis. Finally, for the third circuit, the internal resistance of the source, the 5 ammeters, and the 2 voltmeters in parallel quite obviously change the nature of our once relatively easy series parallel circuit into a serious boss-level challenge. Trust me, you'll want to wear a bulletproof vest and some night vision goggles to fight this tiger. Despite the sheer volume of crap jammed into this single circuit, this should still be well within your reach if you're organized and consistent. Current through elements in a series path is the same. Voltage across paths in parallel is the same. What goes up must come down. What goes in must come out. Visualize this circuit at the nodal level from the perspective of flowing current. I'm asking what the ammeter and voltmeters read at their given locations. There are some obvious disclaimers about what the instruments are actually reading. We'll discuss these subtleties in the analysis. Our first circuit incorporating the non-ideal instruments and sources can be visualized as such. Source current will flow through the internal resistance of the source, through the internal resistance of the ammeter, then split between R1 and voltmeter 1, rejoining, then splitting again between R2 and voltmeter 2. The 4 kiloohm voltmeter in parallel with the 90 ohm R1 makes this combination approximately 88 ohms. The parallel combination of the 180 ohm R2 and the 4 kiloohm voltmeter 2 makes this combination approximately 172.2 ohms. The VDR, Ohm's law, and/or KVL can be used to determine the voltage drop across all elements. Where the voltage drop across the internal resistance of the source is approximately 0.87 volts, the voltage drop across the 10 ohm ammeter is approximately 1.74 volts, the voltage drop across resistor 1 and the voltage read by voltmeter 1 is approximately 15.35 volts, and the voltage drop across resistor 2 and the voltage read by voltmeter 2 is approximately 30.04 volts. Ohm's law can be used to determine the current through each element, where a source current of 174.36 milliamperes travels through the internal resistance of the source and the ammeter. Notice, however, R1 truly only experiences 170.54 milliamperes because 3.84 milliamperes of the incoming 174.36 milliamperes is diverted through the voltmeter. Similarly, notice R2 experiences only 166.87 milliamperes of current because 7.51 milliamperes of the incoming 174.36 milliamperes is diverted through the voltmeter path. Notice even with these subpar instruments, the ammeter is still experiencing current very close to our ideal conditions, and the 2 voltmeters are reading values very close to ideal conditions. The differential between the ideal and true observed values can be explained using instrument loading effects in your previously obtained electrical circuit analysis skills. Our second circuit incorporating non-ideal instruments and sources can be visualized as such. Source current must travel through the internal resistance of the source and the ammeter used to measure source current. From here it splits into 3 paths and rejoins. The current through ammeter 1 is equal to the current through R1. The current through ammeter 2 is equal to the current through R2. the summation of these three branches is equal to the source current. The voltage drop across these three paths will be the same. This path can be combined in series, something I'll call R prime, with a value of 130 ohms. This path can be combined in series, something I'll call R double prime, with a value of 250 ohms. These three paths can be taken in parallel into a simplification I'll call R triple prime, with a value of approximately 83.7 ohms. Now, the VDR, Ohm's law, and/or KVL can be used to determine the voltage drop across the internal resistance of the source, the ammeter, and R triple prime. Where the voltage across the internal resistance of the source is found to be 6.08 volts, the voltage across the ammeter used to measure source current is 12.15 volts, and the voltage across the three paths making up R triple prime is found to be 101.77 volts. Since R1 and R2 are in actuality elements within the series paths R prime and R double prime, we need to use the voltage divider rule to solve for the actual voltage drop experienced by these resistors. The VDR set up to solve for V1 is as follows. Substituting in the necessary values, we find V1 to be approximately 93.94 volts. The remaining approximately 7.83 volts must be dropped across the ammeter used to measure current through R1. The VDR is set up to solve for V2 is as follows. Substituting in the necessary values, we find V2 to be approximately 97.70 volts, meaning the remaining approximately 4.07 volts must be dropped across the ammeter in this same series path. Notice theoretically, voltage across elements in parallel should be the same. However, due to incorporating non-ideal instruments, notice that V1 is different than V2. The voltage across the two paths is still the same at 101.77 volts. However, voltage distribution within the two paths is ever so slightly different because of the non-ideal effects of the instruments. We can now use Ohm's law to determine the current through each element. Source current traveling through the internal resistance of the source and the ammeter used to measure source current is approximately 1.22 amps. Ammeter 1 and R1 experience the current of 782.8 milliamperes. Ammeter 2 and R2 experience a current draw of 407.1 milliamperes. And finally, the remaining 25.4 milliamperes is leaking through an unintended path through the voltmeter in parallel. Notice the difference between ideal and observed source current, ideal and observed current through R1, ideal and observed current through R2, ideal and observed voltage drop across R1, and ideal and observed voltage drop across R2. Because of the non-ideal nature of the instruments and their placement within this circuit, our observations are notably departing from our expectations. And we used our previously obtained electrical circuit analysis skills to explain and account for these differences. Our third circuit can be visualized as such. Notice I've taken the internal resistance of the voltmeter used to measure the voltage across the R1-R2 pair and placed it on top. Source current must travel through the internal resistance of the ammeter used to measure source current. Then it will split into three paths. One through the voltmeter I'll call VMX, the second through the series combination of ammeter 1 and resistor 1, the third through ammeter 2 and resistor 2. These three current paths rejoin and then split again into three other paths. One through voltmeter Y, the second through ammeter 3 and resistor 3, the third through ammeter 4 and resistor 4, and then rejoin. This series combination I'll call R prime with a value of 110 ohms. This series combination I'll call R double prime with a value of 130 ohms. This parallel combination of three paths I will call Rx with a value of approximately 58.7 ohms. This series combination I'll call R triple prime with a value of 210 ohms. This series combination I'll call R quadruple prime with a value of 190 ohms. This parallel combination of three elements I'll call Ry with a value of approximately 97.3 ohms. Now, the VDR, Ohm's law, or KVL can be used to solve for the voltage drop across all components: internal resistance, ammeter source, Rx, and Ry. The voltage drop internal to the source is determined to be 1.05 volts. The voltage drop across the ammeter used to measure series current is 2.1 volts. The voltage drop across the three parallel paths called Rx is determined to be 12.36 volts. The voltage drop across the three parallel paths called Ry is determined to be approximately 20.49 volts. The series path R', consisting of ammeter 1 and R1, has a drop of 12.36 volts, and the voltage divider rule can be used to solve for the voltage drop across R1. The VDR setup to solve for V1 is as follows. Substituting in the necessary values, we find V1 equal to approximately 11.23 volts, meaning the voltage drop across the ammeter used to measure I1 is approximately 1.12 volts. Using similar techniques, we can solve for the voltage drop across resistor 2 to be 11.41 volts and the voltage drop across the ammeter used to measure current through resistor 2 to be 0.95 volts. Notice V1 and V2 are different from each other. However, the voltage drop across the parallel paths, R' and R', are equal to each other. Voltage division within those paths is ever so slightly different for resistors R1 and R2 because of the non-ideal effects induced by these ammeters. Similarly, we can determine the voltage division within the R' path and the R' path. V3 is found to be 19.51 volts, and the voltage drop across the ammeter used to measure current through R3 is found to be 0.98 amps. The voltage drop across resistor 4 is found to be 19.41 volts, and the voltage drop across the ammeter used to measure current through R4 is found to be 1.08 volts. The voltage drop across the parallel paths, R' and R' are the same. However, voltage division within those paths show that V3 is ever so slightly different than V4 because of the non-ideal nature of the ammeters in series with R3 and R4. Finally, we can use Ohm's law to determine the current through every component, including source current. Source current traveling through the internal resistance of the source and the ammeter used to measure source current is 210.5 milliamperes. It splits into three paths, 112.3 milliamperes of which goes through ammeter 1 and R1, 95.1 milliamperes of which goes through ammeter 2 and R2, and 3.1 milliamperes of which goes through voltmeter X. These three paths rejoin and then split again into three alternate paths, 97.5 milliamperes of which travel through ammeter 3 and R3, 107.8 milliamperes of which travels through R4 and ammeter 4, and 5.1 milliamperes of which travels through voltmeter Y. Alright, that is it. We are finally done with this example problem. Compare and contrast some of the electrical properties we would expect to observe using ideal instruments on the left-hand side versus what we obtained when we accounted for some of the non-ideal natures of the instruments and sources. It's not like we're on a different planet or a different country or a different state, but we're definitely in a different county or at least the town next door. However, any error in our position can be accounted for using basic electrical circuit analysis and theory. In closing, I'd like to leave you with this seemingly contradictory observation. I've built a very simple circuit using circuit simulation software. Notice the ammeter is observing a small amount of current through this circuit despite the fact the switch is open. What on earth is going on here? I've been telling you the whole time that current does not flow through an open switch. Has the circuit simulation software gone mad? Have I been lying to you the whole time? Or has this lecture provided you with the necessary skills to root out and resolve this contradiction? Think about it. The answer is right in front of you. In conclusion, this lecture took an introductory look at instrument loading effects and how the act of measuring an electrical quantity can influence a circuit's behavior. You'll be overjoyed to realize that a well-constructed ammeter or voltmeter should not unduly or excessively influence a circuit's behavior, and any effects can be considered negligible for our purposes. This discussion, however, presented us with the opportunity to employ our series parallel circuit analysis skills on increasingly complex series parallel circuits. You should have appreciation for the complexity behind the simplifications employed in circuit analysis, and you should be able to account for minute differences observed in the course of study using previously acquired circuit analysis skills. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.